Also, last time we went through this slide set number 7. We just started it, but we didn't continue because of time. So what happened when you have compression steel? I'm going to call this to be compression steel. The symbols that we're going to be using here is going to be AS for the tension steel, and once you see this prime, AS prime here, it means it's giving the compression side. For example, tension steel AS, depth to tension steel is going to be D. Compression steel AS prime, depth to compression steel is going to be D prime. Now, in this case, it's going to be kind of similar to the T section. What's the similarity here? We're going to have two compression forces. These two compression forces is going to be kind of similar to what we have done in the T section. I'm going to put quick here the T section, just to remind you. So in here, I'm going to have two forces. And again, I'm going to have ZF and ZW. In this case, I'm not going to call it here CF and CW because this is still a rectangular section. I don't have here a T section. And in this case, I'm going to call this to be C1, which is the main compression force in the concrete, and C2 is going to be the compression force in the steel. Very similar also to what we have done in the T section. I can simply here say that C1 plus C2 is going to be equal to the tension force.
Is F prime for the steel, so for C2, that's
Yes.
going to still be, that's still
Yes.
going to be the tension, the one for the steel?
So this one here is going to be for the tension, and it's going to be for the compression, right?
Okay.
So I'm going to be going in detail through this.
Oh, okay. I'm sorry.
No worries. No worries. You're good. So now I have the parameters for the section itself. Now I need to look at the strain distribution. Strain distribution, when you have this positive moment, like what we usually use, it's give you your neutral axis, right? Above neutral axis give you compression, below neutral axis give you tension. So I can come here and say this give you tension, and above is give you the compression side of the beam. So I'm going to see here compression. So okay. The 0.03 is give you the point at which the concrete is failing, and this give you like the limited state. If you want to determine again the capacity, usually you just take this as 0.03. This where the concrete fails and the beam is not active anymore. At the bottom, this give you the tensile strain. Absolute S is give you the strain in steel. Strain in the steel right here. And the top is give you 0.03, which is the compressive strain in the concrete. Right? At the same level, I can figure out the strain in the compressive steel. So the compression steel is going to be taking absolute prime M, absolute prime S, excuse me. So here I have AS prime, D prime, absolute S prime. This gives you the compression strain in the compression steel. In our analysis, when we have just rectangular section, we said that let me assume here that this absolute S is going to be more than the yield. And if this give you the case, the stress in the steel is going to be equal to F sub Y. Say, yeah, I remember that.
Yes, we do.
Yeah. So here's what happened in the past. Previous slide said. Here's the tension. We assumed that the strain in the steel, epsilon S, is greater than or equal to epsilon Y, which is yield strain, the 0.0021 for grade 60. If this happens, Fs is going to be equal to Fy, and this tension force is going to be equal to F sub Y times As. Same here. If you assume that the strain in the steel, in the bottom of the steel, is going to be more than the 0.002, which is the yield strain, the tension force is going to be equal to As times F sub Y. But I'm not sure in this case if it's going to be yielding or not. So I'm just going to say it. Let me put it here in generic format. I'm going to call it times Fs. So instead of calling this to be epsilon Y or more than epsilon Y, and this Fs to be equals to F yield, I'm just going to call it for now Fs, and this is going to be epsilon S. Can do the same thing also in the compression steel. So it's going to be epsilon S prime, and the stress in the top steel or compression steel is going to be Fs prime. So as you see here, anything here that's going to be in compression is going to have this prime thing. Even the concrete stress. You see the strength here in the concrete is called F prime C. prime is going to be for compression, and C is going to be for concrete. Now let me look here at the forces. At the bottom, the tension force is going to be AS times FS. As we said, let me not call it here F sub 1. Yeah. For the compression force, I'm going to have the main compression force for the depth A, compression block depth, which is equal to C times beta 1. And this force here is going to be equal to 0.85 A prime C, which is the stress, times A times the width B. Yeah, I have it. So this is going to be the main compression force. The new component force that I have, because of this compression steel, is going to be equal to AS prime, which is the cross-section area of the top steel, compression steel, times FS prime. That I don't have it yet. In an ideal world, I'd like the bottom steel to yield and the top steel to yield, so that all the values is going to be simple. I can just solve it quick. In the T section, I'm taking here back to the previous lecture. In the T section, I have this ZW and ZF. In here, I'm going to have to C1 is going to be called Z1, and to C2, the distance is going to be called Z2. This one, there's no change in the way that you do it. It's going to be equal to the depth minus A over 2. Because from here to there, it's going to be equal to A over 2. But this Z2 is going to be equal to D minus D prime, which is some simple numerical values that you inhabit. So before you start the problem, you need to know where the top reinforcement is going to be, where's the bottom reinforcement is going to be. So if you know the clear cover here and the clear cover on the top, is D prime, and from the bottom, it's going to be so simple to figure out D and D prime, and therefore also Z2 is going to be simple to find it out. There's no problem with this. The standard problem here is going to be the steel. Is it yielding or it's not yielding? Whether it's going to be the tension steel or the compression steel. The performance of the steel, top or bottom, is going to be the same. What do I mean by that? The stress-strain relationship for the steel is going to be the same. This relationship from the previous slide, number 1. Stress versus strain is going to be the same whether you go in compression or tension. There is no problem. It's going to be exactly the same. All right. So when I look here, I said, okay, now I'm going to have a few variables that I'm going to be having some trouble with. The first one that I used to solve in an easy step is going to be A. So how do you do this A? You find out tension and compression, you set them equal to each other, then you find out A. The problem in here that you don't have this Fs. You don't have it yet. But usually we assume it's going to be equal to Fy. And then we confirm it's going to be, actually the steel is going to be really yielding when you check the strain in the steel, and then you say it's going to be more than 0.002, 1 for grade 60. So I'm going to have here one issue. This is going to be the second, and this epsilon or Fs prime is going to be the third one. So 3 variables that I really need to work on it, right? It's going to be A, compression block depth. Fs, you want to be sure that this is really yielding, and also Fs prime, you'd like this to be yielding, but in many cases it doesn't yield. And this is where you need to go the extra step. But at any point, at any time, you can say T is going to be equal to C1 plus C2. Just to remind you, if Fs is going to be lower than F sub 1, if the steel is not yielding yet, I'm going to put this slide back. If we're still within this range, the elastic range, and you want to find out the stress in the steel, which is your Fs, this one, or Fs prime. What you need to do is to find out the strain in the steel. So the strain in the steel is going to be one major issue. Once you find it, it's going to hit here, intersect with this line, right? And once you get there, you're going to be drawing here this line like this and find out the stress in the steel. We'll just take this epsilon S, which is the strain here in the steel, multiplied by 29,000 K psi. What's the 29,000? The steel modulus elasticity. Okay. So for Fs prime and Fs, in both of these two cases, if the steel is not yielding, I need to find out the strain, epsilon S and epsilon S prime. How do you find it? You can say, well, if you know that's going to be 0.03, you know the depth C, with these two similar triangles, you should be able to find out the strain. Sounds easy, but let's see some example. Before we do this example, I'd like to take this set of forces and start to split it. So I'm going to say this A and B, which means the section and the strain is going to be exactly the same. Nothing will change here, right? The strain at this level is going to be equal to epsilon S, and based on this, you should be able to find out the stress in the steel. Same thing in the top. You know the location of the rebar, and you know the strain distribution, so you can find out epsilon S prime, and then based on this, you find out Fs prime, which is the stress in the top steel. So what we decided, if you look here, I have here three figures or three graphs, 1, 2, and 3. Here I'm going to have 1, 2, 3, 4. These two graphs, these two illustrations, is going to be actually for the force. So look at this: section, strain, force. Section, strain, force, and force. So what happened? I know that the total tension is going to be equal to the total compression. C1 plus C2 is going to be equal to the tension T. So what we decided to do is to take this tension force, split it into two forces. This T1 plus T2 at the end is going to be equal to the force T. So I can say here the force tension, which is A sums Fy or Fs, equals T1 plus T2, which is the same as C1 plus C2. You guys follow? Yeah, it makes sense. It's the same steel, the same tension steel. It didn't change. You cannot say a couple of rebars is going to be for this, two other rebars. No. You just take the total cross-section area and then say, I'm going to split it into two forces. Why would you like to do that? Because you'd like to split each couple to be like a separate couple. Here's one couple, and here's going to be the second couple. The first couple, you're going to have here a tension force T1 equals to C1. And this is going to be for the compression in the concrete. The second couple here is going to be to balance the effect of the compression steel, which means T2 here is going to be equal to C2. You can see here C1 and C2 didn't change. If I may go back one slide, C1 is a 0.85. This is going to be the concrete compression force. And C2 is going to be the compression in the steel, in the compression steel. So it didn't change. Even the equation didn't change. The problem here, how do you find out T1 and T2? You say, well, if I have the C1, I'm going to be taking a fraction of the steel, sum of the steel at the tension side, multiplied by the same Fs. So you take this AS and split into two portions. You can say one piece is going to be here, AS1 and AS2. When you add AS1 plus AS2, you're going to end up with AS, which is the same AS that you started with. So, okay, now I guess it makes sense. I'd like to split it into two couples, so it's going to be easier to handle. And if you like to find out the moment at the end of the day, you're going to say you're going to have Mn1 plus Mn2. Total moment is going to be equal to Mn1 plus Mn2. How do you find out Mn1? T1 times this Z1. Mn2 is going to be T2 times Z2. So fine. So all what I've done, just split it into two components, two forces. And each force and the other one that balances it is going to be like a separate couple that you can work with. So first, I'm going to start that the bottom steel is yielding. And once I start by this assumption, I'm going to put this F to be F sub Y. Because now I assume that the steel is yielding. In the top, the steel is not going to be yielding. And this is going to be most likely the case. I mean, usually top steel is not yielding, you know. I said, good, all right. Now let's see what I can do next. And the best way is just to put an example, numerical example, so that it's going to be like more understandable. Any questions here before I continue?
So you mentioned that you had to split the
Tension
FY
force.
between the two. So how do you know how much is split between the two?
Okay, I'm coming to it. Right, absolutely.
I'm sorry.
No, this is fine. I'm happy that you're asking questions. I'd like to hear lots of questions before we start the example. This is a very good question, actually. How much would you put here? How much would you put there, right? I said portion of the steel is going to be here, portion is going to be here. So how much on each side? I'd like to hear other questions. No, nothing?
All good here.
For are we able to find T2 first if we have the value of F prime C, and then we use the similar triangles to find T1?
Yeah. We're going to do something very similar to that. You're going to see it in a second.
Okay.
Very good.
And then just to follow up, then we would go over to that steel couple, and then we would
Yes,
find
this one. Yes.
Okay.
Yes. So I guess I'd like to hear from you guys if anyone here doesn't like to consider that maybe this steel is yielding and also the top steel is yielding. Would anyone be against this? Or you prefer if everything is yielding and we just use F sub y instead of running through the strain? Am I correct? Just to make our life easier. Yes or no? Or you don't care?
No, yeah, that would be the easiest.
Yeah, this is gonna be nice. So first I'm gonna assume that this is yielding and also the top is yielding. If I assume that this is yielding and this is yielding, what is gonna be AS2 in your opinion? You're gonna say AS prime Fs, which is now is gonna become Fy, is gonna be equal to AS2 times Fy. Therefore, AS prime is gonna be equal to AS2, correct? Both top and bottom steel is yielding. This AS2, which is a portion of the total steel at the bottom, is going to be equal to AS prime, which means the top steel. Simply, AS2 is going to be equal to what? To this reinforcing in the top. Why? Because I just assumed that the steel is yielding top and bottom. How about AS1? I'm going to say is equal to the balance, which means equal to AS minus AS prime. Does it make sense? Yeah? No?
Yeah.
So my first assumption that I'd like to go with, I'm going to say steel is yielding top and bottom. Therefore, AS2 is equal to AS prime. And both of this AS1 plus AS2 is going to be equal to AS. So if you want to find AS1, what do? You subtract AS minus AS2, right? Which means you find the difference between AS and AS prime. The first component of AS is going to be equal to the difference between AS and AS prime, which is right here. The second component of this AS is going to be AS2, is going to be equal to AS prime, the top reinforcing. This is just because we're going to be assuming at the beginning that the steel top and bottom is going to be yielding. Okay, an example. It says, compute the moment strength Feynman for the beam having cross-section as shown, 11 by 20 for the depth. It's going to have bottom reinforcing 3 number 11, 4.68 square inches. So this is good, right? 2 number 8 is going to be 1.58 square inch. Would the clear distance help me in any of this analysis or not really? Yes or no? Do I need this clear distance in any of my analysis?
Isn't that the same as the clear cover on the top and bottom?
Yeah, but do I need it in my analysis?
Just to find the D and D prime.
But D was given right here.
Okay, then.
And
no,
D prime is given right here. So I don't need to spend the time and try to find out H, which is the total depth. I don't need any of them. I have D prime. How about the size of the stirrup? Do I need it? I'm guessing no. The information I need for this problem is going to be this information, right? B and D prime, the depth, AS prime, and AS. Good. Now at the beginning, let me assume the top and bottom steel is yielding. So in the top, you're going to have Fy, in the bottom, you're going to have also Fy. And in this case, AS1 is going to be equal to the difference between this and that, right? And AS2 is going to be equal to AS prime, like what I've done here, right? So now let me do it here, right? And say, let me do the analysis. AS2 is going to be equal to AS prime, which is 158. And AS1 is going to be equal to the difference between the two cross-section areas. Difference between this 468 and 158. So okay, it's going to be like 3-1. How about AS2 again? It's going to be equal to 158, which is the top steel, compression top steel. If you have here AS2 and AS1, I'm going to go back here one step. I'm going to say, let me set this T1 equals to C1, to the compression force. Here's the compression force, and here's the T1 force based on F1. Based on this, if I set this equal to each other, I can solve for A, compression block depth. So I'm going to be doing it. Find out this A. It's almost 3.98. Let's go here through all of these values just to confirm. 3.1 is going to be 3.1 is going to be AS1, as you see here, right? It's not the entire cross section. This cross section area of the steel is going to be only the balance between the top and bottom reinforcing. 60 is going to be this F sub y, yield strength. 0.85 F prime C is going to be 5 KSI, and the width is 11 inches. Let me confirm this. Is the width 11 inches? Yes. The grade is 60? Yes. I said, okay, good. Now I have A. Once you have A, you can do also the C, the depth of the neutral axis. It's going to be A divided by beta 1. Beta 1 here is 0.8 for 5,000 PSI concrete. Now I have the depth of the neutral axis C. This is very good news, right? Now I need to confirm that the steel is yielding top and bottom. So I need to find out the strain top and bottom. Here is the strain at the bottom. How do you find out the strain at the bottom? This here is going to be 0.03. And how much was the C? Let me go back here. C equals 498. So I'm going to put it right here. This C is equal to 4.98 inches. How do you find out the strain at the bottom? You say 0.03 divided by 4.98 equals the strain at the bottom divided by D minus C. Okay, it's right here. Same equation we used in the past, which is this one here. Excuse me. It's going to be this one here. I'm trying here to check the strain at the bottom first. So here's the strain at the bottom equation. 0.03 divided by C multiplied by D minus C. And here's the strain at the bottom. The bottom still is yielding. Look at this value here, 0.09. This is good value. So we're good. Bottom still is yielding. How about the top steel? Can I say, let me find out the strain here, epsilon S prime. I can say 0.03 divided by 498 equals epsilon S prime divided by C minus D prime. And D prime is 2.5 inches. That was given to me. Let me confirm this. Yes, D prime is equal to 2.5 inches. That was given to me. So great. Now let me figure out the compression strain, or the compressive strain. Epsilon S prime divided by C minus D prime. Where is this C minus D prime? It's going to be this distance from here to there, right? C minus D prime equal to 0.03 divided by C. Excellent. How much now the strain in the top steel? 0.0015, below the yield point. I was hoping it's going to hit this 0.021 or 207, right? But this is lower than the strain for the yield point. So this is not good. It means my assumption was incorrect, partially. My assumption for the bottom is yielding, this is good. But in here, my assumption that the top steel is yielding is not good, because it didn't really hit the yield point.
Can you explain one more time why we want both to yield?
What is what? I'm sorry.
Can you explain? Sorry, my sister's over there.
It's all right. No worries.
Can you explain one more time why we want both sets of steel to yield?
Yeah, very good question. Yeah, thank you. Let me take you back here. In this analysis, you're going to have here how many variables we said? 3 main variables. Because someone's going to say S prime is going to be given to me as numerical value, right? B is going to be the same. D prime is the same. You're going to have it. AS, you're going to have it. D, you're going to have it. So to finish all of this analysis and find out the moment, capacity, You need A. Am I correct? Is it one of the requirements or no? You don't need it.
Yeah, because you need to multiply by 0.0.
Because you need to find, yeah, you need to find out this, right? And you need to find out this, and you need to find out this, 0.85. So A is critical. Also, I need the Fs prime for the compression force in the steel, correct? This give you one main component. Also, I need this Fs at the bottom. At the tension steel, I need to know how much is stress in there. Otherwise, how do you find out this T? So now I have three components that I really want. Otherwise, I cannot find out this Vmax. So I'm going to say if Fs prime and Fs is equal to Fy, I'm going to have only one unknown component. And this is going to be very similar to what we have done here. You remember this one? How did we start the whole thing? We said, let me set here the stress in the steel to be equal to F sub y, solve for A, and then after that C, then find out the distance D minus over 2, and then here we go, I have the moment equation, right?
And then
So
when
this, yeah, go ahead.
sorry, when Fs is either equal to or greater than F sub y, we know it's yielding anyways.
Yeah,
Okay.
this is also a very good question here. Now let me put it here for you. Yeah,
since we're
it's
going
gonna be like follow this. Here is the strain in the steel, right? At the yield point, right? And here is the strain itself, the value in the steel is gonna be somewhere here. If the strain is gonna be here, you're gonna say the stress in the steel is gonna be equal to Fy. You see, this is gonna be flat.
Yeah.
So once the strain is gonna be bypassing this value here, absolute Y, which is a 0.021 for the grade 60, you're just gonna take the stress in the steel of Fy. If it is lower than epsilon Y, it means the stress in the steel is not really 60. It's gonna be something lower than this, right? Based on this slope or based on this modulus elasticity.
Yeah, that was my other question, because I know we want the strain to be greater than 0.002. But do we need to know that value where it's...
We don't know it yet. So we're going here through steps. So the first step, I need to start with some assumption, right? So I said, let me assume that the strain in the steel, compression and tension is going to be going beyond the yield point. And therefore, let me assume here that the F in the steel is going to be equal to F sub Y. Now I need to confirm my assumption. So when I did the analysis here, for the tensile strain at the bottom, that was greater than the yield strain. So this is good. My assumption for the bottom steel, yeah, this is going to be at, I'm going to say this is good, this is going to be at Fy. Based on this analysis, because I found out that the strain in the steel, based on this analysis, right, is going to be right here. It's going to be right here. The strain is going to be high strain value. So I'm good. I'm going to be at Fy level. But for the top steel, when I did this quick analysis, the strain is 0.0015. What does it mean by 0.0015? It means that you're here. You're somewhere here, right?
Mm-hmm.
So the stress in the steel is not going to be really equal to 6 KSI.
So we just have like additional steps.
So this analysis, so this analysis is incorrect, because this analysis assumes that the tensile and compression steel is going to be yielding.
Oh, okay.
So now I said, well, let me rewrite the entire equations, right, in kind of generic format.
No
Ready?
problem.
Are you guys ready for this generic format? So okay. Now, you know the tension is going to be equal to compression. So the tension force is going to be equal to C1 plus C2. And you guys, you have seen this before, right? You can say, yeah, this is going to be coming based on this. Tension is going to be equal to C1 plus C2. Now, I cannot split the force this way, right? And assume that here I'm going to have F sub Y and here I'm going to have F sub Y. If you like to split it, this is going to be F sub Y, but this is not F sub Y. You need to be careful about this. So I said, if I'd like to put it in a generic format, I'm going to say tension force is going to be equal to C1 plus C2. And they have all of these terms, ASFS. Now, in this case, it's going to be Fy because the bottom steel is yielding. Top steel is not yielding yet. So it's going to be AS prime, FS prime. And compression, the concrete is going to be 0.85 F prime C A B. Let me just put the whole thing in the same equation. I said, okay, good. Let me put it there. Here is C1, compression of the concrete. And here is C2, compression in the top steel. And this gives me the tension. And I know that the tensile steel is already yielding. So this equation is good. So, okay, good. Don't forget, I have here three variables, right? I have Fs determined to be equals to F sub y. I have Fs prime, and also I have A. So this is now is going to be the two variables, A and Fs prime. It seems that I need two equations, right? To solve for two unknowns. Because A and Fs prime, they affect each other. So I cannot just throw a value there. I need to solve this equation, and I need to have another equation for it. The other equation is going to be based on the strain compatibility, which is this strain equation that you guys have seen, right? You're going to say here, the strain of the top divided by C equal the strain of the compression C divided by C minus D prime. So this is going to be the exact equation that I need to use, and here is my equation. Here is the strain of the compression steel, right? It's going to be this one here, based on this compatibility, or the similarity between the two triangles. If you take the strain in the compression steel multiplied by ES, you're going to end up with the steel stress on the top. So yeah, this makes sense, which means using this equation here. It's going to be using this equation, or using this chart. Come here with your strain in the concrete, in the steel, find out the stress in the same steel, which is this equation here. So this now is going to be Fs equation, Fs prime equation, right? It's going to be just one simple equation. Also, I know that A is going to be equals to beta 1 times C. So look what I'm trying to push this at. I'm trying to put this as only a function of C. So I can take this equation, take this Fs, replace it with this term. Replace it with C minus D prime, C and ES. It means now I get rid of this Fs prime. It's going to be only one equation, which is the C equation, right? It's going to be in C. And this A, I'm going to remove it and instead replace it with beta 1 times C. So the entire equation here is going to be a function of C. So you can rewrite the equation. You take here this 0.85, right? F prime C times B times beta 1 times C. And instead of A is going to be now beta 1 times C, which is this term here. Fs prime, I can take it from here. It's going to be this equation here, right? Look at this equation. It's going to be exactly the same as this equation. And of course, you're going to multiply by AS prime, which is right there. So all what I've done, I've taken this equation, replaced Fs prime with this equation, and replaced A with beta 1 times C. Can I clean the equation a little bit, right? Just clean it. What do you mean by cleaning it? You see here, I have C, I have divided by C. I'm going to multiply the whole equation by C. So look what happened. I'm going to have here a C, C squared, nothing here. So I'm going to have my equation is going to be in terms of C squared, C, and a constant. Okay, let me also clean it a little bit. Let me write all the terms. And then at the end, if you use here ES of 29,000 KSI, which is this ES, with this equation, you're going to find this beautiful equation. This equation is going to be good for any beam with some compression steel, provided the bottom steel is yielding. If the bottom steel is not yielding, it's going to be a different story. But here, this provides the bottom steel is yielding. Once the bottom here steel is yielding, you can safely use this equation. So this equation is going to be in your like formula sheet. You don't really need to drive this again. So once you prove to yourself that the bottom steel is given, which is the tension steel is yielding, you can just jump and use this equation. You don't really need to drive it for me each time that you do a homework or exam problem or a quiz. So, okay, here's my equation. Where's the unknown? What are the known factors? I'm gonna say you have B, right? It says 11 inches. Yeah. I have beta 1, which is a 0.8. I have a prime C. Yeah, it's gonna be 5 KSI. So I have all of that except for this C squared. I say, okay, everything here multiplied by C squared. How about in this term here, 87, AS prime? You have this value. AS prime is the 158. AS, you have it 468. FY, 60 KSI. C, your variable. 87 D prime, 2.5 inches. AS prime, 158 equals 0. Let me take all of this value, substitute in this equation, and here's my final equation that I need to solve. Don't forget that this C here is neutral axis depth. It is not the C that goes in this quadratic equation, right? So I want to be sure that you guys are not confused between this C and between that C. This C that you're looking here at is actually this term, which is negative 9.19. So for this equation here, when you have quadratic equation, A is going to be equal to, now this A, this is not the compression block depth. This is A for this, all of this quadratic equation, right? This A is going to be equal to 1. B is negative 3.83. It's going to be your V value. And this is going to be your C value, negative 9.19. Now solve this equation. You're going to have your two answers, right? One of them is going to be negative, which doesn't make sense because neutral axis depth cannot be a negative value. And the other one is going to be 5.5 inches. So here we go. Now we're able to get the actual neutral axis depth. What should I do next? I guess I need to find out the strain top and bottom in the steel. I said, okay, to find out the strain, now let me look at this. Now you have A, and then you have here the strain in the steel at the bottom. How much is it? It's right here. Look at this value here. Still good. So I'm still good. How about the strain on the top, which is this item here? The strain on the top, I said, well, look also at this equation here. Fs equals to what? From this equation is equal to C minus D prime. Yeah, now you solve for C, C is going to be 5.5 inches times 0.03 divided by C times ES. This is going to give you the stress in the steel directly. So, okay, let me try this. Here's the equation. Now I have the steel stress on the top is going to be 47.47 KSI. At the bottom is 6 KSI. Why? Because at the bottom I have yielding. So this Fs is going to be equal to Fy at the bottom steel. And the top steel is going to be 47.47. I said, great. Also, when the steel at the bottom is yielding, what phi factor do you use? It's going to be 0.9. How about the steel on the top? If it is not yielding, should I reduce the phi factor? I'm going to say no, because this check applies only for the tension steel. This phi factor is going to be for the tension steel, not the compression steel. Now I guess I should be able to find out C1 and C2 and T. Now where are these equations coming from? Look at this. You say, okay, let me go back here now, this slide number 10, and go back here for quick and look at my equations. Where is C1? 0.85 A prime C AB. Where is C2? AS prime times FS prime. Now the new value, which is 47 and fraction KSI. How about the tension force? I'm going to say equals AS times Fy because I know that the bottom steel is yielding. So I say, okay. Let me find out here C1. Yeah, 0.85 A prime C A and B. Now I have all of these numerical values. C2, now I have Fs prime, the 47, and AS for Fs prime. And AS prime is going to be the 158, the 3 rebars on the top. Was it 3 or 2? 2 rebars on the top, right? 2 rebars, 2 number 8, 158. And the tension force, take the bottom reinforcing, 3 number 11 times 60 is going to be 280. Now do a quick check. Do you think that this tension force is equal to C1 plus C2? Can someone help? Is it close or almost the same, engineering wise, or there's a big difference? Someone help? Put C1 plus C2, compare it to this value. Close?
The same.
Almost the same engineering wise, right? So
Yeah.
this is good, a good check that you can do for yourself. If you find out that there is a big difference between C1 plus C2 when you compare to the tension force, something's wrong. This rounding here is just approximation. It is from the approximation that we kept on doing here. So it's not really an error, it is more of approximation when you round the up. So now I have all the forces. Now I need the Z distance. Okay, how about Z1 is D minus A over 2 for the first compression force in the concrete. How about Z2? How do you find out here Z2? You're gonna say D minus D prime. I'm gonna take you back here a few slides just because of the picture. So, okay, now I'm gonna have here two moments. The first moment equals Z1 times C1, or T1 if you like. I'm gonna call it here C1 because I have the value of C1 calculated. Also, I have C2 calculated. So I'm gonna say here Z1 is D minus A over 2 for the concrete compression. And for the compression in the steel is gonna be D minus D prime. It's gonna be Z2. Now I'm gonna have here two moments. Mn1, just add here Z1 times C1. And Mn2, which is C2 times Z2, you have these two values, add them together in this equation, just add these two moments to each other, and then divide by 12, and then multiply by the phi factor. And with that, you have the compression forces in both the steel and the concrete, and you have the tension force, right? In the bottom steel, the tension steel. And in this here, you're gonna have the flexure capacity of this beam, which is 373.16 square foot at the end of the day. Questions? Yes, I'd like to hear questions from you guys.
So you said C1 plus C2 should equal E, but they can be off by like a little bit. Like, what's the max difference that we can have? Could we be off by 2 kips, or is that too much?
No, it's gonna be too much. Maybe like in this case here, maybe 0.1, 0.2, max maybe 0.3 kips. Okay. More questions?
I have a quick question.
Yeah.
When you're comparing like the 0.079 or and the 0.002, where did the second number come from?
This one? Or this one?
The second one.
The second one. Thank you. Good question. I'm gonna take you back here to the stress-strain relationship for this thing. I was trying to find out this yield strain, this point. How much is this? So I said this equation is good. What equation? I'm gonna say here, ES is gonna be equal to F sub y divided by the strain at the yield point, right? It's gonna be the slope of this line is gonna be equal to E. I said this is strain here is gonna be equal to the y component divided by the slope of this line. It's gonna be equal to Fy divided by ES. So I said for this steel it's gonna be 60. KSI divide this by ES, which is a 29,000. In my analysis, it was about 0.02. I want you now to try it on your calculator and tell me what value you get. If you do 60 divided by 29,000, how much do you get? Yes?
Yeah, it's the same number.
So I'm gonna come here and say this is gonna be the steel, yield, strain, which is this value here. And then we can put a box around it. So we know where is this value about, what is this about. All righty. Some people just call it 0.0021. This is gonna be acceptable. No problem with it. So let's say if I'm doing here some analysis and the strain in the steel is 0.00205, I'm gonna say, yeah, this is yielding. I mean, difference is gonna be very small. I'm not gonna repeat the whole thing and redo all of that just because of that, right? You can see this is good. The steel is yielding. Once it goes above 0.002, you can say the steel is yielding. Don't forget that we are not mathematicians who do engineering design. Keep this in mind. Now, let me do here There's a bit of discussion, like side discussion on this. What happens if the bottom steel is not yielding? Here, in this example, the first example that we have done for the concrete design, the steel with this amount of reinforcing, the steel was yielding, and we were able to confirm this. You remember this discussion? We have this assumption that the steel yield strain is going to be exceeded by the actual strain in the steel, which is 0.05 more than 0.02, right? So we said we're good, and everything was great. Now, when we added lots of reinforcing at the bottom, and then we checked for the strain in the steel, it was not yielding. So our assumption here was incorrect. I'm talking here about the tensile steel. I'm not talking about the compression steel. Now it's giving the tension steel. So we have to do here two equations just for that. And based on these two equations, we were able to solve for C and for the strain in the steel, which turned to be lower than the yield strain. And also we did also this FS. Now what I want you to do is to think about what's going to happen if you have here lots of steel at the bottom. It means the steel top and bottom is not yielding. And in this case, I'm going to have three equations. And if you have three equations, right, for these to be able to solve for the three unknowns. In our case here, in this example provided, Fs turned to be equal to F sub y. I assumed something and it happens, so I said I'm going to have here two unknowns. I need here two equations. But in a case like this, I'm going to have Fs, Fs prime, and A. And in that case, if this is going to happen, that the both top and bottom steel is not yielding, I'm going to have three unknowns, and I need three equations to solve the three unknowns. How about if also I have a T section on the top of that? So compression in the concrete is going to be two forces, C web and C flange. Okay. So in this case, I'm going to have four unknowns. Let me show why I'm going to have here four unknowns. In the previous T section analysis that we have done, we have this trouble here, right? With this A2. So we're going to have more than one unknown, right? It's not going to be just two or one. No, we're going to have more than one unknown, and then it's going to be slightly tough. Now, what I want you to do also is to work on a spreadsheet for this problem here, just to make your life easier when it comes to homework. At least you do it once, you can use it maybe 2 or 3 times. It does mean that this spreadsheet can be used during the exam. In the exam, you're going to have formula sheet, and then you need to do everything by hand. You cannot use your computer for this. Any questions? Yes? No? Should we talk about the project?
Yes.
Okay. Now I need to design the beams. Now you guys, you design the slabs. I need to design 2 beams. Here's one beam. I'm going to call this B1. This also is going to be called B2. Now, when I assign this, I'm going to tell you exactly how much width. What is the equation to use it to do the width of the flange? And you're going to end up with something like this. Now, this is going to be our practice to do this type of analysis, right? You're going to have B1 and B2. How about the depth of B1 and the depth of B2? I'll give you this. This is going to be 24 inch. The slab thickness, which says going to be equal to 8 inches. And you have the load already. You have the dead load and live load. Don't you guys have it? Can someone help me here? How much was the dead load? How much was the live load? Yes.
110, Yusuf.
Dead load for the slab design?
110 and 65 for the live load.
Am I correct? Is everybody using the same values?
Yeah.
Okay.
Yes.
Now, I don't anyone to use different values. Everybody's going to be using exactly these two values. Even if in your submittal, for the first submittal, that use different values. This is what you need to fix yourself and use it in any other submittal. This is going to be your dead load for the slab and live load for the slab. Now I'm thinking, how about this beam here? If I'd like to do this beam 1 and B2, how much is the dead load is going to be? You can say same dead load, this is good. But where is the self weight of the beam itself? How about the live load? How much is the live load? And when you do this beam here, how would you do the analysis? Let's say here's the beam, right? We're going to have supports like this. When you're doing the slab, you have taken a strip of 1 foot, right? The width of the strip was equal to 1 foot. How about here, in this case? Now I need the load to be as in P left, pump linear foot. So I need to find something that we call here tributary width. For the beam. So how much is this tributary width of the beam of B1? And how much is tributary width for beam B2? Let's say B1 supports the load. So I'm going to be taking this on the side. Now let me move this box. I'm going to say support the load from here to here, right? To the middle of that distance between the two beams, right? So if you take the slab span, which means from here to there, divide this by 2, this area here is going to be supported by beam 1. And for beam 2, it's going to be supported the distance from half the way between the two beams all the way to here. Does make sense? So if this is going to be 28 divided by 3, how much is that? 28 divided by 3?
9.33.
9.33 feet divided by 2. This is going to be this tributary width for this B1. How about for B2? How much is the tributary width?
9.33.
Exactly. Thank you. Now, how much is the load in B1 and how much is the load in B2? Say load in B1. How did you hear the load in B1, right? So we're going to say load in B1. Let me write it here. Let's say W dead load for B1, right? Equals. You're going to be taking here the uniform load, the 110 times 9.33 divided by 2. So I'll take here tributary width multiplied by the uniform load. So here's the uniform load for that load. And this is going to be tributary width, 9.33 divided by 2. Let's say, how about W live load for B1? Same thing, 65 PSF times 9.33 divided by 2. Let's say, how about W dead load for B2? 110 times 9.33. How about W live load for B2? It's going to be 65 times 9.33. Does it make sense? Yes? Now you understand the story of this tributary width? Yes or no?
Yes.
Okay, great. Is this the only dead load? Am I missing anything? I'm going to say yes, you're missing the self weight of the beam itself. So I said, well, I need to consider this. I cannot just ignore it. So I'm going to say, I'm going to go here to one of this T-beam section that I'm talking about. And let's say that this gives you something like for B2, right? I'm going to throw some numbers. I'm going to say slab thickness is 8 inches. So let me put it here. This is going to be 8 inches. Total depth, which means from here to there, right? I'm going to say this distance here, I'm going to be taking it as, let's say here, 20 inches. Now let's talk about the weight. When you have done the weight here, you have done the weight of the slab. This weight here is going to be for the slab. So I need to say this is going to be the slab load.
Wait, Professor, why is it 20 inches, the total depth?
It's given. It's going to be given to you.
Okay.
Do you have it written here somewhere? No. So we need to decide on this. I'm going to put it 20 inches once I submit. Once I put the submitter requirement, I'm going to put that's 20 inches. Okay. So this weight here doesn't include the weight of the beam itself. It just includes the weight of the slab. Now, where's the weight of the beam? So someone's going to say, when I did here distributed width, I have taken the flange, which means the slab weight includes this box. Therefore, if you like to do the weight for the beam, you need to do it only for this section of the beam. You don't do it for the entire depth of the beam, right? Otherwise, you're going to be having this area of an overlap. We're going to say now it's going to be 20 inches total minus 8. You're going to have your 12 inches of concrete multiplied by the width. We're going to say here, I need to add the component of the beam weight. So we're going to say here, the width is going to be 12 inches times the depth of the beam from the slab is going to be 12 inches. I need to put this in terms of square feet. I'm going to divide by 144 times 150 pound per cubic foot for the concrete weight. You're good? Yeah? No? I can repeat the same thing exactly. I can just take this, copy, and put it right here for B2. It's going to be exactly the same thing because beam size is going to be the same. How about when you do the analysis, how much is your B1 depth and B2 depth? The depth of B1 and B2. Can someone help me with this? You can see here depth. You can say for B1 and B2, depth equal to how much? This depth, roughly. Is it 12 inches? Or it's going to be the whole thing from the top compression to the tension? It's going to be this distance, right? You can say roughly
1875.
20 minus 2.5. How about that? Yeah, 17.5 inch. So when I was doing the weight, I did the weight only for this bottom portion because this slab was already considered in the slab weight, right? I did it already in the slab weight. If you recall this, and I did the slab weight and I did the tributary width. This tributary width includes the entire slab thickness, which means I have considered this piece already. So the remainder that I did not include, that I'd like to include here when it comes to the weight of the beam is going to be only this piece. If the whole thing here is 20 minus 8 is going to be equal to 12, correct? This piece here, the depth is going to be 12. This explains here this 12 inch. About the other 12 inch, I'm going to say this is going to be the width of the beam. Divide by 144 to put it in square feet. Multiply by 150 unit weight of what? The concrete. So at the end of the day, your number that you're going to be getting here, whatever number, is going to be as in PLF, pump linear foot. Divide this by 1,000 to put it in kip linear foot. Are we good? Any questions? Yeah, we're gonna have hooks in the beam, ties. We call this ties, but it's not gonna affect your design when it comes to the tension steel and compression steel later on.
Will it affect our depth D at all?
Would affect what, B or D?
D as in dog.
No, because it will affect it. And when I give you the number, I'm gonna give you here a clear number. I'm gonna say 2.5 inches, right? I'm gonna put this as 2.5 inches. Just to make it simple. Otherwise, I'm gonna have 10 different answers, right? From each one. I don't want this to happen. I'd like just to make it simple in answers. So I'd rather give you this somehow. If I give you this 20, I'm gonna put here in the picture that's gonna be 2.5. It says give you now 17.5, like in this equation.
Perfect, thank you.
No problem. Any questions? All right, go ahead and please sign out. Unless you have a question, you can stay around. The whole thing here, the entire lecture is recorded, so it should be useful. So before you start to work on this, be sure that you back check all of these numbers and you review them before you start your submittal.
Have you started correcting the first submittal?
No, not the first submit. No,
Okay.
very soon.
Professor, is only Excel uploads okay, or do you want to have us show handwritten work?
You cannot just upload Excel, and I'd ask you please to go back and look at the lectures. We discussed this issue, and we said if you just give me Excel without writing the equations, it wouldn't be accepted. Writing the equation means that it needs to be typed. I need to look at it and then say, here's the answer, as if you're handwriting it or you're typing it. So some people just do an Excel spreadsheet, and when they do it this way, you can see all the equations embedded in there, and then you cannot really understand how he has done it. And I'm not interested in back checking your spreadsheet and see if it works fine or not, but I'd like to see the equations written because you need to show work, right? If this makes sense.
Yeah. Okay. So in that case, I only sent for the last upload. I only uploaded just the Excel spreadsheet. So can I send you my handwritten work also, or like resend it with the equations on it?
All right. You have your time here. Please submit it as typed and please in written. And please, just you guys know, if you are not submitting the entire submittal in the way that I have asked you to do it, it is going to be considered as if you did not submit it, right? So be sure that every time you do this, and this is not just for you, this is for everybody here who's listening to me, right? So please be sure that you do the complete submittal and not just give me a spreadsheet and you say, hey, enjoy your life. No, it's not going to work this way. I'm just going to assume that you didn't submit anything. Just skip it. That's all.
Okay.
All right?
Understood. Would you like, are you going to reopen the submittal, or would you like me to email it to you?
Email it to me. But please, I don't want everybody here to send me an email. Here's my new submittal. No, it's not going to work this way. It's going to be only one time, please. Because the problem when I receive it via email, it takes a few steps to put it within the group. So it is not like an easy step that I can just take it and use it, right? Okay.
Yeah. Okay.
Thank you.
Thank you,
All right.
Professor. I'll
Thanks.
be sure to
Okay.
submit it correctly next time.
All right. No worries. Just do it correctly. All right, guys.
So on the Excel sheet then for future tense, is it okay if we just write it out in the style next to it and then just put the answer
Yes.
after it?
Yes, you need to write it next to it. This is what I'm saying. This is absolutely correct. You're right.
Okay. All right. Perfect.
Professor, sorry, quick question. So you are still going to be resubmitting or posting up the submittal number 2 prompt, right?
Yes, I will.
All right, sounds good. Thanks, Professor.
Thank you. Good night.